In today's lesson, we will learn about the two basic concepts of the computer vision, which is the first one is the camera parameters, in which what is the parameter involved in order to relate from the real world environment to the CCD screen. And then the second one is the calibration, one of the important aspects that you need to know if you wish to develop some perception algorithm that able to understanding about the environment and then relate that thing inside of the cameras, such as the robotic application. They need to pick up some object on top of the table. So the robot at that particular case, the perception level should able to know the coordinate from the environment and then coordinate inside of the cameras, and then how it can be related to ensure that the smooth movement of the robot hand. So basically, we go to the basic concept of the camera model first, which is, in this case, the camera model will be based on the pinhole cameras. So if you still remember about our concept of the pinhole cameras, we have the principal axis in which we have some object in the environment, outside object, and then the object will be plotted, will be projected on the screen, which is inside of the cameras via the small hole that known as the pinhole. So for this particular case, the distance from the hole to the object in the environment will be known as the Z. And then later on, the distance from the pinhole to the screen, to the camera screen, will be known as the F, which is the focal length of the camera. So basically, so for this particular case, let's say this is the real world coordinate, in which this is the X direction of object in the real world environment, and also this is the Y direction. So if we look at from our cameras, inside of our camera, we will have almost the same object notation inside of the screen. Only in this particular case, it will be projected in the different coordinate. So in this case, let's say we take X as a U, and then in this case, the Y as V. So in general, we can actually relate this thing directly by using the triangulation concepts, in which if we use the triangulation concept, we can easily obtain, for this case, F over V equal to whatever in the inside. So if this case is U will be over X, and also V will be over Y. So this is actually the basic notation of the triangulation concept based on the projection of the pinhole cameras. So this particular equation can be rearranged. Let's say if you wish to determine the value of U, so U can be easily determined by using Fx plus Z, which is the bigger capital X over the capital Z is actually the real world coordinate, and also for the V will be the same thing. So this transformation can be arranged into the matrix coordination, in which we will have this particular equation. So for this case, we have the focal length. The focal length, by assumption, the focal length for X and Y axis will be the same for this particular case, but it is not the same in the real application. I will show you later on. And then from this homogeneous coordinate transformation, we have another parameters, which is the center of the coordinate. Center of coordinate can be simply determined by adding some sort of the translation parameters. So why we add this thing is because of, normally in the real world coordinate, in the lens, when we get the information, so for this particular case, the center of the projection will be 0, 0, and then right side will be positive, left side will be negative. The same thing will be the top side will be positive, and then downside will be negative. However, in the image, usually the image coordinate system will be something like this, means that 0, 0 will be the center, the 0, 0 will be the left side, and then it will go, this is the width of the image, and then this is the height of the image. So if we wish to translate from this lens projection onto the image notation, so that we need to add some sort of the center image coordinate to the mapping. So basically, this is the recap of what you have learned previously regarding the pinhole cameras, and how it can be assimilated, or how it can be used in order to project the 2D image on top of the screen. So in a simple notation, the projection of the image, which is from the real world coordinate. In this case, this is the real world coordinate to the camera screen. It must be via two parameters. So the first parameters will be based on the extrinsic. Extrinsic means that the parameters that are able to relate between the real world coordinate to the in front of the cameras. And then second one is the intrinsics. Intrinsics means that from the in front of the cameras to the our CCD screen. So basically, extrinsic stands for the external. Ex is the external parameters. So for the extrinsic parameters will be the rotational parameters. R stands for the rotational, and T stands for the translational. Whereas for the intrinsics, the F will be the focal length of the cameras, and then OX, OY for this particular case is the center projection of the cameras. So basically in the following slide, I will show you some sort of the roughly introduction about how we're able to get this particular perspective transformation model. So this is just the recap. As I mentioned previously, we have two types of the parameters that are able to relate from the real world coordinate to the in front of the cameras and also eventually on the CCD screen. So basically the first one is the extrinsic. Extrinsic means that the external parameters, intrinsic means that the internal parameters. So extrinsic will be highly depends on the camera location, means that you put the cameras in different arrangement, then it will be you need to obtain back the extrinsic parameters. Whereas for the intrinsic is highly depending on the cameras. So it means that if you have calibrated the cameras, you obtain the intrinsic parameters, then the parameters can be used for other type of application without recalibrate again. However, for the extrinsic, if you change to the new location, you need to perform the calibration again. So basically, intrinsics, you need to do the calibration for every different model of the cameras, so that the ID or the intrinsic ID for every parameters usually will be unique. So this is how the way the coordinate was transformed. The first one from the world coordinate to the camera coordinate. This is what I mentioned as the in front of the cameras. So this is what we call as the extrinsic parameters mapping process. And then the second one from the camera coordinate, which is in front of the cameras, to the image plane. This is usually this part will be in the real world unit, let's say centimeter or meter. The same thing, which here is centimeter or meter. So once you plot that thing on the CCD, means that this is more on the pixel coordination. So once we put that thing into the image coordinate plane, so we need to use the intrinsic parameters to know the relationship between them. So for the extrinsic parameters, so it will comprises of the two main components. So the first one is the translational. The second one is the rotational matrix. So both combination of this thing is something like this. So means that, let's say this is the so this is the coordinate of the object in the real world. So this is the coordinate in front of the camera. So this is our cameras, for instance. So if you wish to map this coordinate arrangement with respect or tailor with respect to the camera coordinate, so instead we need to perform some sort of the rotational and then translational to move this thing to this side. So this is the meaning of the extrinsic parameters. So in a simple metric notation for this particular case, XC, YC and ZC is the coordinate in front of the cameras, and then XW, YW and ZW is actually the coordinate of object in a real world frame. So basically this is the series of the rotational and the translational parameters that can be utilized in order to map from the real world objects to the in front of the cameras. So the second part is the intrinsic parameters, which is the internal part of the camera parameters. So it will be comprises of the three main components. The first one will be the perspective projection, which is the focal length of the cameras. So the second one is the transformation between image plane coordinate and the pixel coordinate. So this is more the if you still remember, we have the center of image parameters, and also we have the mapping between the, because of the real world is more on the real unit calculation, which is the centimeter meter, whereas in front of the camera the notation will be in terms of the pixel. So there must be some transformation they're able to convert from the centimeter meter to the pixel. So that is the parameters that we use in the second step. And then the third one is the geometric distortion introduced by the optics. There will be two types of the distortion that I will go in details later on. So for the intrinsic parameters, so the first step is the mapping from the in front of the cameras to the CCD. So basically XC, YC and ZC is the coordinate in front of the cameras. If you still remember, we have some object. So in this case, we have the ZW, YW, ZW, which is the real world coordinate. And then we have our cameras here. So in front of the camera here, we have the XC, ZC, and then YC. So now we want to map between in front of the cameras to the CCD. So the first one is we can simply use the triangulation concept, as I have mentioned previously. So this is the determination of this equation is pretty straightforward by using the triangulation concept. So in general, the XP is the coordinate inside of the cameras, which is in the pixel notation. So in general, the XP can be determined easily by using the fx, which is the focal length of the lens of the cameras, and then it can be simplified. It can be simply obtained by multiply this thing with xc over zc. So this is the first step in which we project in front of the cameras to the CCD. And then the second one is that if you look at the transformation matrix here, so we have two different type of focal length, which is the fx and fy instead of a single focal length. So basically, in general, if the projection in the CCD, if the projection is perfect, then we can obtain the square. But in general, in practical, usually in the CCD, the projection is rectangle, which is in this case we have some sort of the fx and fy. So the imperfection of the projection, that's the reason that we have the two different value of the focal length for this particular case, which is the fx and fy. So the second part, as I also mentioned previously, we have the center of the projection. So this is the reason because of in the case of the lens, the center of the projection will be center of the lens, whereas in the image, your origin of the image will be in the top left side. So there is one of the reason that we need to add some sort of the parameters, which is in this case the displacement model of the center projection. So we just simply put the thing as the OX and OY. So in a simple notation, we can represent the matrix of the focal length and also center of projection by using this type of the notation, in which the XC, YC, ZC is in front of the cameras, XP, YP is the inside of the cameras CCD. This is the in front of the cameras, and then this is inside of the cameras, which is based on the pixel coordination. So in general, if we wish to relate these parameters to the real world coordinate, then if you still remember, we have the extrinsic parameters that we have obtained from our previous notation of the rotational and translational. So we can easily plug in that value in the XC and ZC equation, so that we're able to obtain the relationship directly, which is this is the relationship of equation they're able to relate between the real world coordinate to the CCD. So this part, the left side is the relationship between the in front of the cameras to the CCD. So we just need to replace the XC with respect to this particular equation, which is the real world coordinate extrinsic value, so that we're able to do the relationship directly. So in general, most of the previous projection by assumption is that the projection will be perfect, means that we obtain the image, we capture the image from the real world environment, and then the image was imaged on the CCD, and it was perfectly imaged. But in real world, in real application, this is not the case, because usually the image will be subject to two types of the distortion. So the first distortion will be based on the radial distortion. So the radial distortion occurs because of the nature of the lens. So let's say this is the object that you wish to project. So in this case, this is the square object. So if the object bypass through the lens, so we have some diffraction effect, in which for this particular case, the square object in the corner of the object, there will be some sort of the curvy effect. So this is occur because of the lens nature. So for this particular case, we can actually obtain the parameters of this thing. We're able to relate between the projection with the radial distortion effect by using this particular equation. So in general, this is the parameter that you will obtain later on during the calibration process. So for this particular calibration parameters, so the R parameters is the parameter that able to relate between the center of the coordinate with respect to the projection value. Let's say you have the projection value here. So let's say you have the center of the image, and then you have some projection value here. So you can determine R by calculate this type of the distance. So this is where we calculate. This is how we calculate the R parameters. So the K1, K2, K3 is actually the constant parameters. So in general, if the value of K1, K2, K3 is equals to 0 or near to 0, so means that we don't have much radial distortion effect. Whereas because of if this part is 0, 0, 0, so means that x corrected will be equal to x. Means that you don't have to do any correction to the projected image you don't have to do any correction to the projected image. However, in a situation where your value of the K1, let's say you have the 0.1 K1, K2 you have 0.2. So for this particular condition, you need to consider to do the correction regarding the projected image, because of for this particular case, your y corrected will be equal to y plus yk1 r squared plus yk1 r double squared. So for this particular case, there is one of the reason that you need to make sure that when you perform the calibration, you need to look at the value of the K1, K2 and K3. So if the value is higher, so means that your camera built in terms of the construction of the radial distortion or the lens used is maybe the cheaper one. So because of that, you have the radial distortion effect that might be quite severe. So in some situation, let's say if you use the fisheye lens, so for that particular case, it is you should note that you will obtain the higher value of K1, K2, K3. And as a result, if you have the higher value of the K1, K2, K3, so for that particular case, you will have the radial distortion effect. So radial distortion effect means that, let's say this is the curvy, the straight object, the straight line on the image will look like a curve because of the radial distortion effect. So for this particular condition, when we perform some calibration process, we will obtain the parameters of K1, K2, K3, and then we can utilize these parameters, all these 6 parameters, in order to reproject the image so that you obtain very nice image, and then you're able to remove the radial distortion effect. So we call this image as the undistorted image. So the second distortion that will occur in the camera is the radial tangential distortion effect. So tangential distortion effect occur because of the imperfection of the CCD installation. So in this particular case, if you have some lens here, so the perfect location of the CCD is supposed to be something like this. So in this case, we're able to make sure that the projection will be perfect in terms of the object in the environment. But usually, some sort of for this particular case, since we put some glue here, so there is some condition that the projection here will actually not really perfect. And then for this particular case, you will have some sort of if this is your image, if your image is under the tangential distortion effect, then the resultant image will be something like this. Means that we have some sort of the distortion in terms of the output value instead of the square. So we obtain something like the trapezoid image. For the equation of the tangential distortion, it will be something like this. For the tangential, the parameters involved is P1, P2. So last time in terms of the radial distortion, it will be K1, K2, K3. And then for the tangential, it will be P1, P2. So it will be in the same condition in which if your P1, P2 is small, so means that X corrected equal to X. So for that particular case, you know that your CCD was perfectly installed inside of your cameras. But in a situation that your P1 or P2 value is not zero, so for that particular case, you will have some sort of this effect when you project the image. But usually, if we perform the calibration process, most of the camera nowadays, the tangential distortion effects is not occur. So because of the installation is almost perfect, so we can try later on by using your camera phone. You can obtain the parameters of the tangential and the radial, whether it's good or not with respect to the given input image. So in general, if we consider our previous equation in which we have the XC, YC and ZC. So if we consider the radial distortion and tangential distortion effects, so we can obtain the XC prime by simply divide the XC over ZC, and then later on the corrected of the projection, it will be based on for every XC and ZC that we have projected, we can just multiply with respect to the corrected value. So for this particular case, the XC double prime is the corrected of the projection value with respect to the radial distortion effect plus the tangential distortion effects. And then later on, we can utilize this equation in order to obtain what is the projection of image on the CCD by considering the distortion effects. So basically, based on the previous derivation of the equation, perspective, transformation, projection, so we can conclude that this is the parameters that we need to obtain. The first one is the intrinsic parameters. Intrinsic parameters will be the focal length, fx, fy, ox, oy is the center of the projection, and then K1, K2, K3 is the radial distortion effects, whereas the P1, P2 is the tangential distortion effect. So this is in terms of the intrinsic parameters. For the extrinsic, we need to obtain two parameters. The first one is the rotational, and then the second one is the translational. So we can obtain this particular information by performing the calibration step. So basically, if I simplify the perspective transformation equation, it will be something like this. So in general, for the camera calibration is a process to estimate the value of the intrinsic and extrinsics by supplying information of the XP and by supplying the information of coordinate inside of the cameras and also the coordinate in the real world application. So means that for this particular case, we just supply this information. We supply these two information. We have these two information. Now, how we able to relate this? If we have this type of information and also we have this type of information, so how we able to estimate what is the value of fx, fy, ox, oy with respect to the supply information from input and output. So in general, the camera calibration is the process to determine the internal parameters of the cameras. So in general, this is the parameter that we will obtain: the center of the projection, focal length, the scaling factor, and also the lens distortion. So this is based on the intrinsic parameters. So the motivation, the calibration is important if you wish to, as I mentioned, we want to develop some sort of the application, they're able to relate between the robot eye to the hand. So we need to know exactly the coordination of the real world environment and also in front of the cameras so that the robot can grasp the object accurately. So in a simple application, we can say that the calibration is, this is the coordinate in the real world environment. You supply the coordinate in the real world environment, sets of coordinate in real world environment, and also at the same time the coordinate in front of the the coordinate of the image inside of the image, inside of the CCD. So if we have this type of information, then we can use some sort of the least square fitting method to estimate the relationship, so that we're able to obtain the intrinsic then and extrinsic parameters. Okay, so this is some sort of the calibration procedure. So what we need to do is that we have the cameras. So usually most of the calibration process will be use the checkerboard. So why we use the checkerboard? Because of the checkerboard will supply you with the consistent pattern of square, in which you need to supply the length of each of the square here, so that this thing is the information they're able to read in the real world. So usually the unit will be in centimeter or meter. So once you capture this image, the checkerboard image, so you can see the checkerboard image inside of the cameras. So let's say only for this particular arrangement, if you pick up this point, you will have this coordinate, but the coordinate will be in the pixel notation, whereas the coordinate in the real world here is in terms of the centimeter and meter. So in order to find all the extrinsic and intrinsic parameters, so you might note that we need to at least have parameters be able to relate that thing more than the required information. So let's say we have around 12 plus the plus 7, so maybe around 20 parameters. So that for that particular case, you need to supply the information more than 20. So this is just for example. You need to ensure that you supply information more than 20, so that you're able to utilize the least square fitting method accurately in order to estimate the unknown parameters. So this is some sort of the process on how we're able to get the position of the checkerboard. So in general, in the calibration step, so let's say if you hold the checkerboard, this is the camera. So you need to make sure that you will rotate the checkerboard. You will move the checkerboard, let's say near to the camera, far from the cameras, and then rotate that thing, and then give some sort of the in the different arrangement. So and then later on, once we have that thing, if we're able to actually get some more possibilities, let's say we cover all the possibilities of the movement of the checkerboard, then we can get almost perfect calibration parameters that able to really be to the real world, to the in front of the to the inside of the cameras. So I just skip this step because of later on I will provide you with some sort of the video on how you can perform the calibration by using two toolbox. The first one by using the MATLAB, and then second one by using the Python. So in general, this is the process that you need to do in order to perform the calibration. So you need to supply with series of the series of image of the checkerboard, and then later on you can use the calibration toolbox in order to estimate the value of the parameters, which is the intrinsic and extrinsic. So basically, when you perform the calibration step, you will be supplied with the matrix P equation. So from the matrix P equation, it can be expand later on, means that P will be consist of these both parameters, the intrinsic parameters and also the extrinsic parameters. So you can extract the information later on, so that you're able to obtain the information accurately. So this is some sort of the step that you need to perform when you wish to do the calibration, in which for this particular case you capture the image from, let's say, different angle, different orientation, different distance, and etc. And then once the corner detected, when we perform the calibration, we have some series of this particular information. So in general, this is the intrinsic. You will be supplied with both information. The first one is the intrinsic parameters, and then the second one is the extrinsic parameters. So for this particular case, I give you some sort of the example of we perform the calibration of the Kinet camera. So for this Kinet camera, you can see the RGB image, the focal length of the RGB image is around 118, and then for the IR, will be higher, which is 580. So this is the center projection of the image. So if you look at this information, you can expect that the actual the actual image dimension will be times 2, which is in this case will be let's say this is 640, so this is maybe 480, more or less something like this. So means that this is the dimension of the image that was projected based on the Kinect camera. So because this is the center of the camera, center of the image, which is here will be the location OX and OY. So you can double that things times 2, so you can get the actual dimension of the image. So for the RGB cameras in general, K1, K2, K3 is the radial distortion. If you look at the parameter is quite good, means that everything is almost 0. So for this particular case, you can say you don't have you have almost nothing about the radial distortion effect. And then the second one, in terms of the tangential, you see this is the power of -3. So the same thing with the P1, P2. So both camera does not suffer with any tangential distortion effects. But for this particular case, if you look at the K1, K2 for the IR cameras, so the value is quite high. So we can say the IR cameras have some issues regarding the radial distortion effects because of the value K1 and K2 is quite high. But no problem, no issues regarding the tangential distortion effect. So the second one is the extrinsic parameters. This is the extrinsic parameters they're able to relate between the left and the right cameras. So in particular, this is the rotational parameters, and then this is actually the translational parameters of the cameras. So you can see this is the actually X, this is Y, and then this is Z. So in general, you can see YZ, so means that your camera was perfectly aligned in general. But in this case, for the X, so we have some sort of the distortion. No, not distortion. Actually, it's more on the translation, the distance between the two. So in the calibration, this was actually in a meter. So if you transform to centimeter times 100, so the distance is around 2.6 centimeter. So what we can say about that thing means that for the Kinect camera, we have the IR, and then we have the RGB cameras. So we can say the center projection of the IR and the RGB so was actually located 2.6 centimeter between both of the cameras. So but in terms of the Y, so means that we don't have any issues regarding this thing upside down. And also if you look from the top view, so this is the way how the camera was arranged, means that it's almost perfect in terms of the Z coordination. So I will show you some sort of the example of the calibration process. So for this particular case, we have the, you can look at the example in our in your Google Drive. So basically, I look at the calibration method, the exe file. So let's say if I use the command prompt to execute this part, you just need to run the main file from this part. I use the command prompt because of I just want to make sure that you can see what is actually, because finally when the training complete, the calibration process complete, it will provide some sort of the value. So this is the example how we perform the calibration from the RGB and also the IR cameras, how we're able to relate that thing, external and also the intrinsic parameter estimation. So there will be some sort of the value here after the calibration step completed regarding the error, regarding the intrinsic parameters, extrinsic parameters, and etc. okay, it will require some times usually to get particular information. Okay, so basically, this is the rotational parameters, which is that extrinsic parameters, the rotational parameters, and then also the translational parameters. So the error is around 0.7 pixel, which is quite good. So we have the same value here, which is the negative 0.026 meter. So this is in terms of the translational, which is able to relate between x and y. So all the information regarding the camera rotational, camera translational, and also the distortion of IR, distortion or RGB, intrinsic and extrinsic parameters. So let's say if we try to open the intrinsic parameters of the RGB camera. So for this particular case, this is the information, which is the focal length of the cameras, and then the center projection, and etc. So this is the arrangement of the value. So once you perform the calibration step, basically you can obtain such information easily. So this is some sort of the revision. So I just put this thing as your task in the Google Drive. So the first question is that you have this type of the problem. So how we're able to briefly explain how you're able to find the distance between two cameras by using what method? And then the second question is that illustrate the rectangle of object shape that is under radial distortion, tangential distortion, and both distortion. So let's say if I try to do this example, so let's say this is your rectangle image, this is your input image. So what is the object shape under the radial distortion? So you will have almost the rectangle, but you have some curve in the corner. So this is under the radial distortion effect. So if the same rectangle under the tangential distortion effect, so in this case we have the rectangle. So if the image is under the tangential distortion, so this will be the effect. And then finally under both distortion, radial distortion plus tangential distortion. So for this particular case, you have the rectangle image. So you have the radial distortion, and then at the same time you have some sort of the tangential distortion effect, but you have more curve in the corner. So this is some sort of the effect of everything. So basically this is the Python setting. If you wish to construct your own camera calibration platform, so I will give you the details on how you're able to set up that thing. So thank you.